so far to harbor life. Like it or not, for the moment, the Earth is where we make our stand.
Hello everyone, hello Space Cowboys, thank you very much for tuning in. This is the first video in what I hope to be a series of conversations with people whose jobs rely on the fact that the shape of the Earth is indeed a sphere. So we're talking anything that uses GPS or any satellites at all, anything that relies on knowing curvature formulas, anything that relies on Coriolis, anything like that. So for the first chat here, we have IB Hunter, who, among many other things, is an astrophotographer, has worked for a marine survey company, and you were involved in the development of 2 GPS correction methods. Is that right?
That's correct.
Excellent. Well, thank you very much for joining me. I really appreciate you taking the time out of your day and having this conversation. First off, I think what I want to mention is just the astrophotography stuff. That blew me away the first time I saw that, because I hadn't really, before getting into Flat Earth, I hadn't really looked into amateur telescope work, and I didn't realize that you could capture images that are as very nearly as spectacular as Hubble photographs on your own. How'd you get into that? Was that a kind of a big process to learn how to do all that?
Sort of. It all started many years ago. I had a telescope when I was really young, and kind of grew out of that for a while. And later, as I was older, believe it or not, I used to go hunting and sitting in the woods waiting for the sun to rise. I would use my rifle scope to look at the moons of Jupiter and the rings of Saturn. And
oh wow!
So I would just sit there waiting for the sun to come up, looking at the stars and all, and that I would just enjoy just being out in nature and everything and doing that. And later on, I started doing a lot of photography. So I had got a DSLR and learned how to use that, and started using it to where doing all the manual settings and understanding all of that, and eventually got to where I was doing some video and photographs of microscopy through my son's microscope. We would actually get stuff out of the streams and little tubs and look at it under a microscope, so I'd take some pictures of that. Eventually I ended up getting a telescope and hooked my camera up to it, and was able to get something really nice right off the bat. It looks pretty poor now, but I was super pumped with it, and it didn't take very long before I was kind of hooked and trying to learn as much as I could. And within 2 years, I had a pretty good little portfolio of what I think is some pretty good images. I mean, it doesn't compare to some of the guys that's been doing it for years, but I was pretty proud of it.
Definitely, I've seen some spectacular ones of yours. You've done some really good images of the Orion Nebula. That one of the Eagle Nebula that you compared to Hubble's Pillars of Creation, that was very cool.
Yeah, well, that's one that's pretty neat, to where you could actually see how detailed Hubble is. I think the Hubble image that was inset onto mine was made up of 16 other images. If you look at the original, it's got all these little squares that are put together around the edge. It's not actually square like that little inset. And though each one of those is a higher resolution than my entire photo is. So the detail on the Hubble is so much greater, but whenever you bring it down to kind of compare it to what you see out of the telescope, the structure is still there. It's still the same, and it overlays perfectly.
Yeah, that was very cool. Very cool. I remember one of your images of the Orion Nebula, it got kind of quote-unquote messed up by a passing satellite. Is that kind of a regular occurrence? Is there a way to account for that at all?
Well, Yeah, in certain areas of the sky, you can expect to have satellites. So if it's along the celestial equator, you're going to have all the geostationary satellites.
Right.
So you know when that's you're going to have those problems and where you're going to have those problems. But there's satellites all over,
Right.
and many of my images are stacked from several minute exposures, and I do that all night, and I may do it for several nights to be able to develop an image off of something. And it's nearly impossible to take a picture of a part of the sky for hours and hours on end without having at least one or two satellites pass through.
Right. It's still spectacular images. It's I find it kind of funny that it in terms of astrophotography it ruins it, but like for the sake of things like my channel, it just further confirms that satellites do indeed exist.
Right. Normally what we normally do is just throw those images out, or if they're not too bright or too pronounced, then we'll just go ahead and keep them in the stack. And when you stack them, it averages out the satellite to where it doesn't show anymore.
Right.
And that's what you're after. But yeah, for this, like what you're doing, that's exactly what you're after, is to be able to see those satellites. And they're kind of hard not to get if you do very much of the astrophotography. Right. If you go and take a couple of photos, more than likely you're not going to have a satellite in it. But whenever you do a lot of long exposures, it's not unusual to catch one.
For sure. That's interesting. Speaking of spotting satellites, I'm curious, have you ever done anything in terms of spotting the station?
I have. It's that's actually a very difficult thing to do, especially with an equatorial mount telescope.
That's what I hear.
It moves so fast. It's hard to do. And my telescope, the lowest magnification I could put on it barely fits the full moon into the field of view. It just barely fits in there.
Right.
And that's the lowest I can go. So my field of view is very small, so it's very difficult to keep it in the field of view without it just zooming right across one way or the other if you're tracking by hand. There's some people that wrote software to help it to where you could guide on the satellite, on the ISS, and track it, and it uses a separate camera at a lower magnification to keep it centered in that smaller one, which keeps it centered in the bigger one.
Right.
And it's able to track the ISS. Yeah. And that's the best way to do it. It's just not very easy to do by hand. I've seen people do it, but my attempts have not been great. I've done it a few times, but not great attempts.
It seems for the most part, the people I've seen who get good images of the station, that's very much a specialty of theirs. So it seems like it requires a lot of work, a lot of dedication to really get some good shots of the station.
Yeah, you're not going to spend a month trying to do that. This is a year or more project to be able to get to where you can get really good stuff. Astronomy Live has some amazing stuff. JW Astronomy has some nice ones too. They spent a lot of time, and they've tracked this ISS many times. So it's not real easy to just go out there the first time and grab it. The one way you can do that is to have a transit where you can actually focus on a spot that it's going to be. So you have a transit over the moon.
Yeah.
I've even seen where there's a transit across Jupiter, where they're focused on Jupiter and the ISS crosses in front of Jupiter.
Oh yeah, I think I saw that. JW Astronomy did that, I think.
Exactly.
That was very cool.
And doing that allows you to have an even tighter focal length, a longer focal length, because you know exactly where it's going to be.
Right.
And that's kind of cool.
For sure. Yeah. All right. Well.
But it's a tracking issue.
Yeah. It makes sense that it would be easier to catch a geosynchronous satellite in an image because they're moving, I don't know, maybe a third of the speed of the ISS, probably less.
Well, a geosynchronous is super easy because you don't even need a tracking mount at all because it stays in the same position in the sky relative to you.
Right.
So compared to you, it doesn't move at all. But
Mm.
the non-geosynchronous satellites move very similar to the ISS. But you catch those in the frame, there'll be streaks across the entire frame. If you do a 30-second exposure, you're going to have a streak all the way across the frame. That particular geosynchronous satellite, the reason why it looked like a streak is because my telescope was tracking the Orion Nebula.
Right. Okay. It was the
So
camera moving, not the satellite.
exactly.
Okay, that makes sense.
And on one of the frames, I showed a zoomed out image from my camera of the Orion Nebula as a small thing with a little red line showing how far the satellite moved in that amount of time in the several minutes that I took those photos. And it was a very small part of the sky, but that just so happens to come out to how much the sky moved relative to the ground, or the Earth rotated relative to the sky.
Hmm. Oh, one other thing I wanted to ask you about astrophotography. I'm not sure if your schedule is allowed for it, but did you happen to catch any good images of the what's the name for it? The Great Conjunction.
The conjunction.
Yeah.
Unfortunately, I am in Houston, and I don't have my telescope with me. I took some with my camera, which in the middle of Houston with the lights on a parking garage, it just less than desirable. But I did catch something. It's you could tell what it is. It's not real great.
Right. That's
So,
fair.
I guess I'll have to catch the next one in about 800 years.
So same for me, unfortunately. Dawson has a really nice celestron, and we tried to get a look at it, but there it was just constant cloud cover all of the days it was happening, so we didn't see much.
Yeah, I kind of expected not to be able to get it based off of what was going on at the time.
Mm-hmm. All right, so astrophotography is one thing, but you said you worked for a marine survey company as well, right?
Yes.
Okay.
We actually surveyed the oceans primarily. We had some land divisions, but we primarily did oceanographic mapping and survey.
Is that like mapping the seafloor kind of stuff, or?
Yeah, we mapped the seafloor, coastlines. We did bathymetry, which is depth mapping. So we'd do these 3D sonar images of the bottom. We would do visual type images from sonar. We would actually map out hazard locations for NOAA for putting into navigational maps. So if there's any hazards in any areas, we'd actually have to georeference all of those hazards for any other ship for navigational purposes.
Okay. All right. I can imagine a couple ways already that would involve knowing that the Earth is a globe, but is there anything specific that simply would not work if the Earth were flat?
Well, first of all, we're sometimes thousands of miles off out to sea, and we have to have accurate position down to a meter or so. And there's just no way of getting that kind of positional accuracy without having GPS satellites available.
Okay.
And even GPS satellites are not capable of getting that kind of accuracy on their own. You have to have a correction for those satellites because GPS inherently has some errors into it.
Right.
You have the orbit errors of the satellite itself due to gravitational differences in different parts of the Earth. You have time correctors, which is drifts of the atomic clocks in the satellites. And then you have ionospheric and tropospheric errors based off of changes in the ionosphere and troposphere. So you need to be able to correct for all of those to be able to increase the accuracy of your position. That's usually done through another satellite, which is a geostationary satellite.
Okay. It's all the corrections are done through a second satellite. That's interesting. I was wondering how the correction was done, if it was all through software or it's just a second point of view that.
Well, sort of. It basically, for the most part, most of them use reference stations on the ground that receive the GPS signal and see what kind of errors it has in it, and corrects for those errors. The very simplest way of doing it is to just correct the range corrections for each one of the satellites. So if this satellite's off by this amount and that satellite's off by this amount, you send those corrections up and goes to your receiver, and it says whenever you receive the signal from this satellite, correct it by this much, and that satellite correct it for that much, and you end up with a corrected position.
Okay.
It gets a lot more in-depth and complicated, where one of the systems we uses each GPS satellite has dual frequency, basically a L1 signal and a L2 signal off of each GPS satellite, and it uses a combination of those two signals that are different frequencies, and since they are different frequencies, they react different in the atmosphere, in the ionosphere and troposphere. And measuring the difference between those two, they can measure the delay caused by the ionosphere and troposphere and take out the biggest error in the GPS signal just by measuring those phase differences between the L1 and L2 signal. And that takes out the biggest problem of it, which is the ionosphere and troposphere error. And then we just send the timing corrector error and the orbit corrector error through a geostationary satellite to be able to relay back down. It's just a set of numbers to correct for the time in the orbit back down to the receiver through that other satellite. So it's not actually using the geostationary satellite to position. It's just using it as a data communication point.
Okay. And you said you were involved in the development of two different GPS correction methods. So that's kind of what we're talking about now. You were involved in two ways of accomplishing this.
Right. One of them was it's kind of continental U.S. And it works very similar and is a predecessor to what most of the GPSs most consumers use right now, which has a WAS differential. It's a wide area augmented system differential. That system uses, for ionosphere and troposphere, is they use a ionospheric map that's developed with dual frequency base stations throughout. Our system preceded the WAS system and worked very similar, and was able to get GPS down to a 1 meter accuracy. We later worked with a different company and was able to get another system that gets down to 10 centimeter accuracy anywhere on Earth. You could go anywhere in the world and have 10 centimeter accuracy GPS.
Wow.
Yeah.
Wow.
It's a pretty impressive system. And it has been tested all the way in the Arctic and in the Antarctic. I have some friends that went down there and did some testing with it.
Oh, that's really cool. All right. Well, two GPS correction methods. A lot of work with marine surveying that relies entirely on GPS existing. Astrophotography that all points to heliocentrism and stellar evolution and everything we know about stars and how they work. And you mentioned marine gyrocompasses as well. You said you worked on them. Is that just you used them, or you worked on the development of them?
I actually worked on the gyros, not on the development, but on the gyros themselves. But on the marine survey, there's so many things that use the shape and rotation of the Earth to operate, and marine gyrocompass is one of them. But it's not just survey that uses this. Practically every ship in the ocean uses a marine gyrocompass as its primary heading sensor. The gyrocompass has a spinning mass in it and a weighted gimbal, and it compares the weight causes a precession whenever the Earth is turning to cause the the moving mass to orient in a north-south direction, and it points to true north instead of magnetic north. And we have to use true north for our maps and everything because it's going to be way more accurate, and it doesn't change over time like the magnetic pole does.
Right.
Magnetic pole actually moves, and otherwise we would have to keep updating these maps all the time. Whereas if we use a reference of true north, all you have to do is update the declination chain. And if all of the ships have a true north-seeking gyro on board, then they don't even have to do the declination change unless they have to use their third-tier backup, which is the magnetic compass. The other issue is you have a steel ship with cargo on board that's steel. You may be passing by platforms which are steel, and all of that will affect the magnetic compass, especially if you're going by any kind of accuracy. So marine gyrocompasses are pretty critical and only work if the Earth's rotating.
Interesting. Very interesting. I didn't know that. I didn't know there was essentially boats rely on the Earth being a globe in the same way that planes do.
Even more so, because the plane could get away with a magnetic compass for the most part, because they're not onloading and offloading huge steel crates and stuff and all, so they could get away with some of that. Now, we've been using fiber optic and laser ring gyros for decades, for a very long time. The fiber optic gyros have been around for a really long time, and we use them not only for detecting change in angle or angular changes, but we'll use it for basically an INS system, an inertial navigation system, or IMU, an inertial measurement unit, to be able to compensate for heave, pitch, and roll on a boat. So whenever you're using sonar to be able to track the bottom, you have to be able to take out the motion of the boat and how that affects the sonar. Otherwise, that would affect the data that you're collecting also.
Right.
So you have to have very accurate measurements of how the boat is moving. The side effect to that is, if you reference that with accelerometers to the direction of pull of gravity, then you actually get a heading off of it as well. So in that way, it works just like the gyrocompass, except you're using a fiber optic or ring laser gyro instead of a mechanical gyro.
Right. Okay. Very interesting. Well, there was one other thing. When you listed off a few of the things that you've done that rely on the Earth being a globe, and you said among many other things. Is there anything in particular that kind of jumps out that you wanted to talk about?
Well, early on, whenever we would position rigs offshore, before we had GPS available, we would use theodolites, and then later on total stations. That requires triangulation from shore base to go offshore, and you could triangulate between all of these rigs, and you always take multiple measurements. You just repeat the measure, basically the same measurement from different positions and stuff to double check everything. The more redundancy, the better. The more you can increase your accuracy or the confidence in your accuracy. And then whenever you have a fairly large grid, like whenever there was a lot of rigs in the Gulf, you end up with some really good measurements on the thing. And if you take triangles through a very long range of where all of these points are, you end up with the spherical excess on these large triangles, which means that you have a triangle that measures more than 180 degrees, which only happens if you're on a curved surface. some of the other things that we do is we've done gravimetric surveys using gravity meters to determine densities in certain areas. So different areas have different amounts of gravity. So the acceleration of gravity changes based off of the density in the area. And using this in conjunction with magnetometers that measure the Earth's magnetic field and sub-bottom sonar that can penetrate the bottom and go many meters below the surface. And, by combining all of this data, the geologists can actually use all of this to determine where it's the best place to drill for oil or gas or whatever. So we've done some gravimetric surveys as well.
Wow. You know, I always find it amazing that flat earthers have this mindset of there is no gravity. Scientists don't even know what gravity is, and they say it's not even a force. And there is a thing called a gravimeter. It exists. It's an instrument that measures gravity itself.
And the simplicity of the instrument there's several types of gravimeters, and the reference gravimeter, the one that you use as your base to compare the relative gravimeters off of, is about as simple as you can get. You actually have a vacuum chamber with a prism that drops through this vacuum chamber, and it uses interferometric lasers to measure how fast it's accelerating. And it's about as simple as you could possibly get. You know, you're just dropping this thing through a vacuum and measuring how fast it accelerates. It's nothing complicated about that at all. But it gives you a really accurate measurement, and you can base your relative measurements off of that. And it's super precise. I've worked with some really precise equipment before.
Well, I have to say, I love all the satellite stuff, because that's always been the strangest claim to me, that flat earthers will say, well, there's no satellites, there's no space. And you remember as a kid, we're brought up learning, like, there's thousands of satellites out there. You can see them all the time. If you see something that looks like a star, yet it's moving against the stars, it's probably a satellite. And then suddenly I find this group that says, no, they don't exist, they're not real. And I found that so strange, because we're brought up to understand that we all use them every day.
Well, there's a lot of things you could say to that, and I've had conversations with several, and there's ways you could test it. I mean, the easiest one by far to see is the ISS, because it's so much bigger than the rest, and it's fairly low. Two people on the ground a known distance apart can measure how fast the ISS is traveling.
Right, it's been done. Yeah.
I mean, there's no complicated math involved. There's a little bit of math, but it's not much. All you have to do is have two people looking, and when it crosses a star, and you just wait for the other person. When it crosses a star, you'll press your stopwatches, and you can measure how fast the thing is traveling. The other thing is, a simple one is, get a GPS, put the antenna out in an open area, and bring a pot and hold it several feet away from the antenna, and put the GPS in a mode where you can actually see the satellites and the satellite strengths and the lock status of each satellite. Almost every GPS I've come across has that capability, where you can see the lock status of individual satellite number.
Okay.
And you can put the pan up until one of the satellites drops out. Oh, so you know where that satellite is. It's between, if you draw a line from that antenna through the pan to the sky, that's where that satellite is.
Right.
And just hold that pan there for a while. That satellite will come back into view to where it's now locked back in. All you got to do is move that pan a little bit more, and it goes back out. So you could keep doing that and actually track its location across the sky as it passes overhead.
Right.
You can track it with nothing more than a GPS and a pot.
Yeah, I like the sound of this test because it completely refutes the ground-based towers argument because you're blocking it between the receiver and the sky. There's no tower there.
And there's nothing that a government agency could do to know that you're putting a pot right there.
Right. Yeah, then you get into some simulation theory type stuff.
Yeah.
To try and explain that away.
It's and the fact that you can see these things all over. Or the other one that is refuted a lot of times is a direct TV satellite dish. You can look that all the direct TV satellite dishes are facing the same direction.
Mm-hmm.
They're pointed to the same. They're actually using 3 satellites now, if I remember right. But they're all pointing to the same direction, same general point in the sky. And the further south you go, the further up they are from the horizon. They're pointing.
To the point where satellite dishes at the equator are pointing straight up, right?
Straight up, and you go south of the equator, they're pointing north. I've spent time in Brazil. I photographed a southern star rotation many years ago, and I was fooling with satellite communications at the time. Another thing is, on a ship, you have a satellite dish. People don't really think about it too much. How do you use a satellite dish on a ship? Because the ship moves, points different directions, and it heaves, pitch, rolls all over the place. How does the satellite dish point to the satellite?
Right.
Well, it's an active dish. If you look at the beginning of my channel, on the beginning of most of my videos, I have a little splash screen, and it's got a picture of a satellite dish with motors on the gimbal mechanism. And that's a satellite dish that's made to go on a boat, where you tie in your GPS, you tie in your gyro, but then it actually points to the satellite it needs to, and then it locks into that satellite. And as the boat moves, the dish moves to keep the satellite in view. And the thing is, you could be on a boat and ride it from the United States all the way down to Brazil, and you could watch that satellite dish move the further south you go. And you could watch it go to where it's pointing directly overhead to where it's pointing now to the north. I mean, it's something we do, Yeah. It's and it's not magic. It's something I worked on every day. So has the gyro. I actually own 2. I have 2 gyrocompasses in my garage right now. It's not rocket science or anything. It takes some work to understand the electronics and the physics behind it, but it's not unattainable. It's something that somebody could do,
It seems like it's something just complicated enough for flat earthers to not want to bother. Like, I often see, whenever I see a flat earther, on the rare occasion that they pick up a telescope, it's just a simple, like, point and shoot, here's what I saw in the sky for 5 seconds. They're not willing to spend several hours doing long exposures and stacking them, and they don't understand how any of that stuff works, and they don't want to take the time to learn, it seems.
It's unwillingness to put forth the effort on something that may prove them wrong.
Right.
So, I've just had a couple of videos released about me just recently, are directed towards me, because apparently my stuff is faked from NASA generated photos, which I took as a compliment. Thought that was one of the best compliments I've had.
I haven't had the chance to watch that yet. Are they basically accusing you of just like going to the NASA website, grabbing some Hubble photos, and saying I took this?
Basically, yeah.
Wow.
Oh, and I was issued a challenge to take if my telescope is better than a P900, which, oh my God.
Which it is.
To take it over a body of water and zoom in across the top of the body of water to the horizon, and I should see land. I said, well, that depends on what's there. He says, but since your telescope is so powerful, you should zoom all the way past that on into space at the horizon, just looking straight out. And I thought about it for a second. I said, well, you don't need a telescope or a P900 to actually look straight across to the horizon and see space. Every time you see a moonset or a sunset, that's exactly what you're looking at, is
Right.
space at the horizon. And I answered him that, and he just really insists that he wants me to point my telescope at the horizon over water, which I'm several weeks away from being home with my telescope. But and I don't have a really good spot to point it over water at the moment, but
Nor much
maybe
of
at some
a...
point I'll get a chance to do that.
Well, you also don't have much of a good reason to. You know full well what you're going to see.
Well, yeah, I've actually used theodolites offshore, so I've actually measured this stuff. So there's not a reason other than, okay, yeah, that throws something else in the folder of, in case they ask, I could show them this. But I mean, I'm not going to go through a whole lot of effort for that,
Right.
because I've done it before. Before Flat Earth was a thing. I actually don't work for the survey company anymore. I work on marine robotics now. So I don't have the same access to the same equipment I had before, or at least the same level of access I had to it.
Well, that's still marine robotics. That's really cool. Is that like deep sea stuff, or like oil rig type stuff, or?
It's autonomous self-driving boats.
Oh, interesting.
Yeah. So we can survey through a radio link to just about anywhere through a satellite link.
Oh, okay. For a
So
second,
we can control a boat.
I was going to make a joke about how I'm sure some cargo captain somewhere is angry that you're going to take his job, but if it's for survey boats, that's a little different.
Yeah, it's primarily, a lot of what we've done is with survey stuff, especially if it's kind of in a dangerous area, or an area where a bigger ship can't get to. We can make a smaller remote controlled boat that can get into some of the areas that's a little dangerous for the bigger boat to go into.
Right.
And we can launch it off of the bigger boat.
Oh.
So it ends up being able to multiply the effort between the two vessels, to where you get twice as much coverage with just one crew.
Yeah. Well, that's very helpful. Anytime we can put a drone or robotic something in harm's way instead of a person, that's always a good thing.
Absolutely.
All right. Well, I think we've covered the big things here. Was there anything else specifically you wanted to bring up or talk about at all?
No, there's a bunch of things, but it's that would be a much longer conversation, I think. So I think that kind of covers the biggest things, or the ones that have the most relevance, I would say.
Okay. Well, maybe at some point we'll get together again. We'll do a part 2 on this. But
That sounds great.
Again, I do really much appreciate you taking the time out of your day to talk to me here and explain some things that were really, really fascinating. I had no idea about... I don't know very much at all about marine surveying, so I feel like I learned a lot today, and I want to thank you for that.
Oh, no problem. Well, I actually would like to do a little more talking with PhD Tony, because we kind of are in the same field, just two different parts of the same field.
Oh, okay.
So he's in the geosciences and geophysics, and we did geophysics survey. So he did the abstract version of the work we do. So
okay.
He would generate the work plans, and we would actually go out and perform the work. So
okay. He was the idea man. You were the implementation.
Yeah, we were the workhorses, the grunts.
Hey, not a bad thing at all. A underappreciated role, to say the very least.
It's extremely interesting work. it's something I've learned a lot from, and it's pretty relevant. I mean, we actually did some stuff that contributes to history. We found the first. We found a German U-boat in the Gulf of Mexico.
Oh wow!
Which there was no historical reference of the fact that there was a German U-boat. There was a suspected German U-boat, but nobody knew for sure until we actually found it. We did work to recover space shuttle parts whenever the shuttle exploded over Toledo Bend Reservoir.
Oh, right. I remember you mentioning that you were involved in the Columbia recovery effort.
Right. I was the tech support out at the shop. We actually had several crews that went out for that, but we supplied all the GPSs for even other crews that went out there, and we supplied some of the sonar equipment, and we actually supplied a couple of crews and went out there and actually surveyed and tried to, and were searching for primarily the data recorder, which ended up being found on land, but we were looking for and marking other places for other debris for divers to go down and recover.
Right. Wow. My webcam didn't turn on, did it?
No.
Okay. I didn't think so. I saw the little two dots in the corner of my screen. I assume it's because I'm running OBS and it didn't want to turn on the camera. Otherwise, I would have shown... I'll just show a picture of it at this point in the video. I actually own a piece of Space Shuttle Columbia's tire from the from the forward nose gear. It's not from STS-107. It's from an earlier flight. I guess they replace those tires every flight.
Very cool.
Oddly enough, I think I looked it up, and the flight that it came from carried a payload for Queen's University, which is in the town that I was born in, coincidentally. So I have a piece of space shuttle history that's actually linked to my hometown, which is really cool.
Well, that's cool. Oh, I have something a little similar to that. One of my videos, or actually two of my videos, I did some work on a lathe to make some parts for my telescope. And the lathe that is used came from Rice University Space Science Center, where students would make projects for NASA that actually gets put on satellites and stuff. So that lathe was used to make some of the parts that were put on satellites.
Oh, that's cool. That's really cool.
Now, even cooler than that is it was actually used to make some of the parts for the prototype ventricular assist pump for heart patients.
Oh, wow.
That one of my son's friends ended up having, or two of my son's friends ended up having ventricular assist pumps put on before they got transplants. So that was very interesting too, and it all came from that same lathe.
So you got a piece of history that not only sent things into space but helped save lives.
Exactly.
That's very cool. That's really cool. I think we're at 43 minutes here. I think we covered a good amount of material here. Any other kind of last minute discussion topics you want to touch on, or maybe plug your channel or anything like that?
Oh, my channel is just IB Hunter on YouTube, and mainly I do astrophotography, and I just posted one video that has not directly debunking flat Earth, but just the closest I've ever come to debunking flat Earth on my channel, as far as putting some of the photos and videos of stuff I've done to compare to what NASA actually says is up there.
Okay.
So it just is comparing what I could get from my backyard to what NASA has. And
I guess you did something. It wasn't in response to flat Earth, but you did something similar before, where you were tracking a Martian dust storm, and you saw the planet clear up over time, right?
Right. yeah, that was that was kind of cool because saw it start to clear up long before the news reports came out. So I was able to tell that it was starting to clear up. So it was.
So we can
And
confirm NASA's not making things up when it comes to Martian weather.
That's exactly right. Well, I mean, and I think a lot of the people, and I've talked to several, and several flat earthers that are actually good people. You could find them. They're not the norm, but
they're few and far between, but they're there.
They're there, and some of them are just misguided.
Mm-hmm.
And if you have a normal, calm, rational conversation with them, no need to be without being
hostile,
rude or insulting. Yeah, hostile. Sometimes they start out that way, but if you keep staying calm, they eventually kind of calm down, and you can actually have a conversation. And one thing I find is that a lot of them don't think that the average person can do these things. They don't think that the average person can verify a photo of that Hubble took for themselves, or they don't think that you can measure how much curve is in 500 yards of water, or one of the things is that there's videos on YouTube that show how to build a receiver and a directional antenna and actually receive data from old analog weather satellites and get real-time imagery as it's passing over your head.
Absolutely.
They have no idea that you could do stuff like that. But you can. It just takes a little work. I mean, I have to stop short of saying it's easy because easy is a relative thing to people, and it does take a lot of work. Sometimes it takes a tremendous amount of work to do some of the things, but it's not out of reach for a person to do. It's just anybody can do some of this stuff. The guy that was posted the videos referencing me, my response to a lot of it was just look through a telescope. That's all you got to do is just make the effort. Go to a telescope shop, and you can tell you where you could go to actually look through a telescope for yourself.
Right.
You know, and it just takes that little effort to confirm that thing one way or another, and then just move on to the next thing and do it. That's why whenever I have discussions with them, and they ask me about how does this work, or what do you think of this, or how does that do, I'll explain to them how it works, but I'll also give them not one but at least two different ways to where they can verify it for themselves with stuff that's readily available that they can get themselves. You can rent a theodolite. I mean, you could get the app, but you could actually rent an actual theodolite. Gyros are rentable, but they're still rather expensive. You can rent a gyrocompass.
I think
normally it's companies that rent them, but it is possible to get them.
I think I know a guy who has a laser gyro for sale, only used once. I think his name's Bob.
See, that was one that's kind of neat too, because he actually used, if I'm not mistaken, I think he used a fiber optic gyro, not a ring laser gyro, and it's made by KVH, and I've used a lot of their products. We primarily use KVH satellite tracking domes, satellite tracking dishes, but I'm pretty sure his was. I suspected it whenever he said it was only $20,000. I said, no, that's got to be a fiber optic. That's not a ring laser. At the time,
right?
I think they've come down since, but the fiber optic has the capability of being more accurate than the ring laser gyros, in the fact that you can just put more fiber optics in it and increase the accuracy more. The advantage of the ring laser is it can have that kind of accuracy in a really small package. So it's I've used them both. I've actually was consulted on some of the power supply systems on one of them that's used one of the ring laser gyro power systems that the company I work for actually sells. And they're really cool. They're small, lightweight. They're kind of pricey for what they do, and they're irritatingly noisy. Oh my god! You don't want to sit by one of those for very long.
Oh, that's funny.
But I used to have a lot of access to them, and if I still had the access I used to have, I would like to. I still can get a hold to one fiber optic gyro that we have, and whenever I get a chance and I have some time, I would like to take it and mount it to my equatorial mount after it's polar aligned, and let it track to where when it's tracking, there should be no motion detected.
Right.
You shouldn't detect a rotation. And then if I stop the tracking, if it's properly polar aligned, I should only get rotation in one field instead of 3 different fields.
Right.
So that would be interesting.
Yeah.
Neat little thing. But it just takes some time and effort that I don't have a whole lot of at the moment.
Fair enough. It's hard to summon the effort to prove flat earthers wrong when they do it so well themselves.
Oh yeah, absolutely. You just have to let them talk a little while, and they'll prove themselves wrong.
Oh yeah, just give them enough rope, and they'll find a way to make it into a noose. So, was there anything else at all? We've got plug your channel. I'll have a link for that in the description as well. Any other kind of announcements or anything you want to shout out before we wrap up?
Nope, I think everything is okay.
All right. Well, once again, thank you so much for taking the time out of your day to chat with me. I really appreciate it. And this is, like I said, this is the first in a series of videos. We may have IB back for a second episode because, as he said, he's done lots of work that very much confirms the shape of our lovely Earth. So with that, I do want to say to everyone, have yourselves a great day, stay safe in quarantine, and I will see you over the curves, Space Cowboys. Oh, I messed that up. I'm not even going to take it again. If you like this video, please give it a like. If you want to see more, please subscribe and turn on the bell for notifications. If you want to support me further, consider becoming a member or a patron, or checking out my merch or my Amazon links. Thank you, and I will see you over the curve, Space Cowboys.
In a vast cosmic arena. Our imagined self-importance, the delusion that we have some